Good afternoon. I'm Mike Solomon, the Rackham Dean and Vice Provost. It's my great honor to welcome you to this year's Henry Russel Awards program and lecture. This is a very special event on the university's calendar. It's the day that we honor a colleague with the highest distinction the institution can bestow, the Russel Lectureship. The 2023 Henry Russel Lecturer is Mark Newman, whom President Ono will introduce to you shortly. I would like to share with you the history of the namesake for the Russel Award. Henry Russel earned 3 degrees from the University of Michigan, a Bachelor of Arts in 1873, a law degree in 1875, and a Master's of Arts degree in 1876. Russel was born in Detroit and remained in Michigan after graduation, where he was a successful lawyer and businessman who was involved with the Michigan Central Railroad, the Michigan State Telephone Company, the Union Trust Company, the People's State Bank, and the Detroit Steel Products Company. In February of 1920, while in New York City, Russel took ill and died at age 67 from pneumonia, just as he was preparing to travel to Europe to bury his son. His son, Lieutenant William M. Russel, was killed in aerial combat in World War I. In his will, Henry Russel left the University of Michigan a $10,000 bequest to create an endowment fund. His one stipulation was that the income from the endowment would be used for additional compensation to members of the instructional staff. In May 1925, the Regents established the Henry Russel Lecturer as a way to recognize a senior member of the faculty with an honorarium of $250 funded by Russell's endowment. In addition, $250 was dedicated for an additional award to honor a faculty member below the rank of professor for conspicuous service to the university. Although the funds from Russell's bequest have long ago run out, the university continues to honor its most accomplished faculty with the award in his name. I'm honored to be involved in today's ceremony to recognize our outstanding faculty members. I'd like to invite Provost Lori McCauley to present the Henry Russel Awards to 4 faculty members.
Thank you, Dean Solomon. There's only one thing better than generating great scholarship, and that's celebrating it with colleagues. It's a joy for me to be here with you to celebrate these accomplishments. Let me start by inviting Professor Andre Leonard to join me at the lectern. Andre Leonard works on the front lines of the quest to develop efficient, affordable, clean energy. His groundbreaking research is helping revolutionize the world's fossil fuel-based energy system to one that is renewable with net zero greenhouse gas emissions. Professor Leonard has developed more efficient methods for generating on-demand electrical power and high-grade heat from solar energy. He has engineered a new high-efficiency thermal photovoltaic cell, a power generating system that converts stored thermal energy to electrical energy as needed. This research has been published in top journals and hailed as a major advance for reliable, affordable electricity. Revered by undergraduate and graduate students alike, he was honored with the College of Engineering prestigious 1938 E Award for excellence in research, teaching, and mentorship. Professor Leonard, in recognition of your transformational efforts to develop reliable, solar-based clean energy solutions that can fuel our nation and the world, the University of Michigan presents to you the Henry Russel Award. Next will Professor Alexandra G. Rosati please join me at the lectern. Alexandra G. Rosati has made remarkable contributions to the understanding of the mind's origins, particularly the evolutionary processes that generate complex thought and biological bases of human cognition. She has shown that species with different natural histories vary systematically in their cognitive capacities, including decision-making, spatial memory, and social cognition. She also has pioneered a comparative development research approach that traces cognition across the lifespan of animals in order to understand the processes of human development. Professor Rosati is a prolific scholar and equally active in the classroom. Her academic awards are many, including a Sloan Research Fellowship, a National Science Foundation Career Award, and an American Psychological Association Early Career Award. Professor Rosati, in recognition of your exemplary contributions to the understanding of animal cognition, both the range of species you study and the novel experimental measures you've developed, the University of Michigan presents to you the Henry Russel Award. Will Professor Kira Thurman please join me at the lectern? Kira Thurman has uncovered more than 100 years of previously unknown German history and revealed the integral role people of African descent played in the creation and performance of classical music. In doing so, she has profoundly expanded and enriched the stories of those from both German-speaking lands and the African diaspora. She is the author of Singing Like Germans, Black Musicians in the Land of Bach, Beethoven, and Brahms. Her book traces the history of Black classical musicians in Central Europe in the 19th and 20th centuries and has been described as an instant classic. It has won 7 major awards and was named a favorite book by NPR. She is a highly respected teacher and a much sought-after public speaker. Professor Thurman, in recognition of your exceptional scholarship illuminating the contributions of Black composers and musicians to German history, culture, and classical music, the University of Michigan presents to you the Henry Russel Award. And now, will Professor Leon Zhao please join me at the lectern? Leon Zhao is a physicist who studies the behavior of millions of billions of electrons using advanced optical techniques to understand how they organize themselves in solids. Her research increases understanding of complex materials and eventually may make it possible to design new materials for specific purposes. Professor Zhao's research highlights since joining the University of Michigan include a first experimental finding of the electric toroidal order and a first experimental realization of the twisted magnet. Her selected awards include a National Science Foundation Career Award, an Air Force Young Investigator Award, a Sloan Research Fellowship, a Macronix Prize from the International Organization of Chinese Physicists and Astronomers, and the Brian R. Coles Prize from the International Conference on Strongly Correlated Electron Systems. Professor Zhao, in recognition of your innovative efforts and significant accomplishments harnessing the behavior of electrons for the advancement of science, the University of Michigan presents to you the Henry Russel Award. And now, our 15th president, President Santa J. Ono, will present the 2023 Henry Russell Lecturer.
Good afternoon, everyone. It's truly a pleasure to recognize these outstanding contributions each of these faculty members make to our understanding of the world. We'll turn now to the Henry Russell Lectureship Award, which recognizes the accomplishments of senior faculty. The recipient is asked to deliver a lecture, which you're about to hear, to the university community. It is an honor to present this award to Professor Mark Newman. I invite him to come forward as I read the citation that he is receiving. Mark Newman is an internationally recognized physicist working in the field of statistical physics. He is one of the founders and most prominent researchers in the area of network science, now one of the largest and most robust areas in statistical physics worldwide. His work brings the mathematical methods of physics to the study of computer networks, biological networks, and social networks, shedding light on the patterns of connection between people and things throughout our world. Professor Newman holds a BA 1988 and a PhD 1991 in physics from Oxford University. He conducted research at Oxford, Cornell University, and the Santa Fe Institute before joining the faculty of the University of Michigan in 2002. He has authored over 180 scientific publications and 7 monographs, including one called Networks, a primer on his research field and one of its foundational texts. At the same time, Professor Newman has been in the classroom sharing his passion for physics with the widest range of students. For his introductory course for non-science majors on the physics of music, to his advanced graduate classes in theoretical physics. His passion is also evident in his mentoring. He has mentored numerous PhD and master's students and postdoctoral fellows, many of whom have gone on to distinguished careers in their own right. Among many honors, he is a fellow of the Royal Society, the oldest scientific academy in continuous existence, as well as the American Physical Society and the American Association for the Advancement of Science. Professor Newman, in recognition of your pioneering leadership and mentorship in network science, a field that has revolutionized our daily lives, the University of Michigan is honored to present to you the Henry Russell Lectureships. Congratulations. Please join me in welcoming the 2023 Henry Russell Lecturer, Professor Mark Newman, who will speak on the connected world, information, epidemics, and the networks that link us together. Professor Newman.
Thank you. Hello. Thank you very much, President Ono, for that very generous introduction. And thank you to the University of Michigan for the tremendous honor of this Henry Russell Lectureship. Looking at the list of previous Henry Russell lecturers is a humbling experience. It's a very good company to be in. I want to tell you today a little bit about the area in which I work and about some of the work that we've been doing here in my research group at the University of Michigan. I work in the field that is today called network science. Although when I started doing this back in the 1990s, they didn't call it that. Actually, they didn't really call it anything. There were about a half a dozen people doing this stuff at that time. I was lucky enough to get in on the ground floor and have had the pleasure of watching it grow from just a handful of scientists to what it is today, with thousands of researchers and journals and giant conferences. So the topic of study here is networks, and for the purposes of this talk, a network means just a bunch of dots joined together by lines. In the jargon of the field, a dot is called a node or a vertex, and a line is called an edge, and I will use that jargon in this talk. There is a long history, for instance, within mathematics, of studying networks. There's a field called graph theory, which proves formal theorems about the structure of networks. But in network science, we have a somewhat different goal. We use these as a tool to represent the structure of a wide variety of complex systems that are of interest to science and human society. Let me give you some examples. This, for instance, is a picture of the internet. The internet is a network where the nodes are computers and the edges are data connections between computers, such as optical fiber cable running through the ground. Many of the questions, the big questions in this field, revolve around the connection between the structure of these networks and their function. How does the structure of the internet, for instance, affect how well it does its job, which is getting data around the world? Here's another example. This is a transportation network. In this network, the nodes are airports, and the edges are flights between airports. Again, you can well imagine that the structure of this network, the way the airports are connected together, is going to affect how good it is at doing its job, which is to get people from A to B. Here's a somewhat more abstract example of a network. This is a picture of a portion of the World Wide Web. In common parlance, we don't really distinguish between the internet and the web. Those are kind of the same thing to a lot of us. But if we're being precise, those are actually not the same thing at all. The internet is a physical network of cables running through the ground. The World Wide Web is a virtual network of information. Its nodes are web pages, and its edges are hyperlinks between web pages. You click on this one, it takes you to that other one. So you can think of the World Wide Web as being an information network in which information is stored at the nodes and then linked together by the hyperlinks. Another example of an information network, one that's very important to us as scientists, is a citation network. If you work in science and you read a scientific paper, like this one here, you go to the end of any scientific paper, it has a bibliography where it references other papers on the same topic. You can take any of those references and you can go look it up in the library, and now you have a connection between that first paper and that second paper. You have two papers, and one of them points to the other one. It cites the other one. Then you can add other citations, you can add other papers, and pretty soon you have a huge network of citations in which the nodes are papers and the edges are one paper citing another paper. Again, it's an information network. There's information stored at the nodes, that's the papers, and then there's the links between the information. Another big class of very important class of networks that we study is biological networks. There's a lot of interest in the biological community in the ideas of network science. Here's just one example of biological network. This is a picture of a metabolic network. That's a network that represents the chemistry of the cell. The nodes in this network are metabolites, i.e. chemicals in a biological cell, and the edges connecting them together are chemical reactions that turn one metabolite into another one. With the rise of so-called high-throughput methods, laboratory methods for measuring metabolic pathways, we now have a lot of data about the structure of these networks, and there's a lot of excitement and hope that a combination of that laboratory data with the analytical techniques of network science could help us shed new light on the very complicated cellular machinery. At the other end of the scale, you can also have biological networks at the organismal scale, meaning the scale of entire organisms. This is an example. This is an ecological network. This is what we call a food web. In sort of lay speak, we talk about the food chain. You know, this species eats this species, this eats this other species, and so forth. But it's not actually a chain at all. It is an entire network, a web, which is what you're looking at here. The nodes in this network are species in an ecosystem, and the edges connect them together are predator-prey interactions. One species eats another species. This is an actual ecosystem that you're looking at here. This is a freshwater ecosystem from a lake in Wisconsin called Little Rock Lake. So it's an actual place, and some ecologists went there and they found all the species and they worked out which ones eat which other ones. And as you can see, it's absolutely not a food chain. It's a food web, a very complicated web of interactions. And then there's social networks, which is a large part of what I work on. If you say the word social networks to most people these days, they tend to think of online social networks, meaning Facebook and Twitter and so forth. And those are good examples of social networks. But to a scientist in this field, the word social networks have a broader meaning. They just mean any network where the nodes are people and the edges are some kind of social connection between people. So that could include online social networks, but it also includes many other kinds of social interactions as well. Indeed, arguably, the sociologists have the longest history of work in this field. They've been doing it, looking quantitatively at networks since at least the work of this guy here, Jacob Moreno, who was a psychologist living and working in New York City in the 1920s and 30s. And as part of his work, he developed these little pictures like this one you see here. It's just a hand-drawn image of a social network depicting patterns of interaction between a group of people. This particular one shows patterns of play amongst a group of children in a schoolyard. Sociologists have been doing this ever since Moreno. Here's an example from sort of modern day version of the same thing. This is a friendship network, again from a school. The nodes here represent students in a US high school, and the edges represent which students are friends with which other ones. Here's an interesting network. I got this one from my colleague Valdis Krebs. This shows, so it's from a study he was involved in about the spread of tuberculosis. So one of the reasons why there's been a huge amount of interest in studies of social networks and a lot of money put into this in recent years is because social networks play a big role in the spread of disease. A disease like tuberculosis is spread when people have close contact with one another. This is a network of who's been in close contact with whom. And the disease spreads over this network, meaning it'll spread from node to node in the network along the edges in the network. So if you know the structure of this network, it helps you say how the disease is going to spread, who's going to catch the disease, how far and how fast is it going to spread. I will say a little more about this connection between social networks and the spread of disease in just a moment. Finally, in this sort of menagerie of networks, here's one from my own work. This is a collaboration network. It shows patterns of collaboration amongst a group of scientists. So the nodes in this network are scientists. And the edges are who's co-authored a paper with whom. This is an interesting network because it's one of the largest and best documented examples we have of an offline social network. Because we have these huge databases of published papers these days. You can just go and get one of these databases and analyze the whole thing and just turn it into a giant network of who wrote papers with whom. Normally, offline social networks are very difficult to measure. It's a lot of work and it's a difficult thing to do. This is unusual in that we have this huge network. There's millions of active scientists in the world. We have this huge network saying, who's worked with whom. It's probably the largest offline social network that we have. There are bigger online ones, but it's probably the largest offline one. Okay, very good. So that gives you a flavor for the kind of systems we're studying. What I want to do with the remainder of the time is, first of all, tell you about a couple of the classic results in this field. And then, if there's time at the end, I want to tell you a little bit about the work that we've been doing here at U of M in my research group. The first result that I want to tell you about is perhaps the most famous one in the field, and you may well have heard of this one before. So this is sometimes called the small world effect. It comes out of a famous experiment done in the 1960s by this guy here, Stanley Milgram, who was then at Harvard University. He was an experimental psychologist, and he was interested, in this instance, in the question of how far apart are people socially? Not geographically, but through the social network, as in, I know a person who knows a person who knows a person who knows you. How many handshakes is it from me to you through the social network? Not an easy question to get at, because we don't have a map of the whole social network. So he came up with a clever experimental way to probe this. What he did was he recruited a bunch of volunteers, mostly from the town of Omaha, Nebraska, and he got them to play a game. The game was, he gave them a letter and said, you've got to get this letter to a designated target person who was a friend of his who lived in Boston. But the catch is you're not allowed to just send the letter straight to the target person. You can only give it to somebody that you know on a first-name basis. So the way you would do this was you would think, well, who do I know on a first-name basis who's closer to this target person than I am? Send it to them. Then they would repeat the exercise. They would send it to someone they know, and so forth. And so cooperatively, via this chain of acquaintances, you try and get this letter to the target person. So the first result of this experiment, as you can probably guess, was that most of the letters got lost, because of course they did. Only about 30% of them arrived, but of the ones that arrived, famous result, it took an average of about 6 steps to get from random volunteer in Omaha, Nebraska, to this friend of Milgram's in Boston. So this is the origin of this sort of mythological result of the 6 degrees of separation, that you are just 6 handshakes away from anybody else in the world. Frankly, this experiment was kind of methodologically dodgy in many ways. It wasn't very well controlled, but the basic idea is widely believed to be true. It's been reproduced so many times with so many different networks by now that we believe the basic idea to be true. It might not be 6 degrees, it might be 4, it might be 8, whatever. The basic idea that you are only a small number of handshakes away from anybody else is thought to be true. In fact, it's not even that surprising. You can make a very simple mathematical argument that sort of explains why this is happening. Suppose everybody has 100 friends. That means the number of people 1 degree of separation from me is 100. That's just the people 1 step away from me, the people I know. And then each of them has 100 friends. So the number of friends, the number of people 2 steps away is 100 times 100, which is 10,000. 3 steps, it's 100 times 100 times 100, which is 1 million. And it's 100 million, and then it's 10 billion. But 10 billion is more than the total number of people in the world. There's only 8 billion people in the world. So that's it. I went 5 steps and I got everybody. I'm done. So there are also some holes in this argument as well, which maybe you have already spotted. But once again, the basic idea is believed to be correct. Fundamentally, what's happening here is that the number of people you can reach is growing exponentially as you go out from the starting point, from wherever you start. And that means that you don't need to go out very many steps to reach everybody. This, it turns out, has a huge impact on all sorts of things we care about. And here's one example. So I mentioned the connection between the structure of social networks and the spread of disease. This is a graph that shows cases of COVID-19 in the US at the beginning of the pandemic 3 years ago. So if you cast your mind back all the way 3 years ago to the beginning of 2020, which is here on this graph, we started to see cases of COVID in this country. So this graph is showing horizontal axis, time in days since the beginning of the year, vertical axis, number of cases we saw. At the beginning of the pandemic, everything we saw was people who caught the infection overseas and then brought it in with them. But starting in February of 2020, we started to see community spread, meaning person-to-person transmission of disease within the country. And once that happened, you start to see rapid increase. You suddenly get a rapid increase of the number of people with COVID. Not only is it rapid, but notice that it also is following a straight line. Now, notice that the axes in this plot are linear axis horizontally, logarithmic axis vertically, logarithmic 1, 10, 100, 1,000, so forth. That straight line on log linear axes represents exponential growth. Straight line says the number of people with disease is growing exponentially. Why is it growing exponentially? It's precisely because of the small world effect. There's some initial carrier of the disease. They give it some fraction of their friends. They give it some fraction of their friends. Because the number of people you can reach grows exponentially as you go out from your starting point, the number of people with the disease also grows exponentially. It does sort of roll off after a while. That's because we had a lockdown. We flattened the curve. But up until that point, clear exponential growth. Okay, so that's one example, classic result in the field. Here's another one. I'm going to introduce this one with a question. How many people do you think you know? Well, let's be more precise about it. How many people do you know on a first-name basis? You would greet them by their first name. You might be surprised to learn that it's a pretty large number. The average person in the United States apparently knows about 2,000 people on a first-name basis. When I first heard that number, I thought that was pretty surprisingly large, but apparently that's the answer. How do they know that? Well, it's not an easy thing to measure, right? You can't just go ask people, how many people do you know? People are very bad at answering that question. So what do? Russ Bernard and Peter Kilworth came up with a neat experiment to get at that thing. What they did was they gave people a list of surnames like this one here. This is the 48 most common surnames in the United States, according to the US Census. And they say, how many people do you know on this list, with names on this list? So that's a question that people are good at answering. And maybe they say, oh, I know 10 people with names on this list. Well, now also suppose that this list represents, for instance, 1% of the total population. People with names on this list are 1% of the population. Well, then you just scale that 10 people up by a factor of 100 and say 10 times 100, that's my estimate of how many people they know. That would be 1,000 in this case. So this gives you a statistical estimate of how many people a person knows. So I quite often do this experiment with students in my class. So I teach a graduate class on network science here at U of M, and I quite often do this experiment with my students. And when I do, it's always the same thing that happens. It's very reliable. There's a lot of people in class who just say, oh, I knew 5 people on the list, or I knew 10 people on the list. And then always there's like one person sitting in the back who puts up their hand and says, I knew 100 people on the list. And the thing is, this is not surprising. This is exactly what you would expect, because it's a distinctive feature of all of these networks that there are always a few nodes that have a very large number of connections. Most nodes don't. They just have a few, but there's a tiny fraction, which we call the hubs in the network, which have a very large number of connections. This was first pointed out by this chap here, Anatole Rappaport. He was a mathematician here at the University of Michigan in the 50s, 60s, and 70s, did a lot of important work in complex systems. I have the honor of holding a chair here at U of M that's named after Anatole Rappaport. He was one of the first people to point out the existence of the hubs in these networks. It doesn't just apply to social networks. It also applies to all the other kinds of networks we look at as well. For instance, this is a picture of the internet again, and most of the nodes in this network have only a few connections around the edges here, but you can see there are a few of these hubs that have a huge number of connections. So that again turns out to be really important. It turns out that these hubs, although only few in number, can play a dominant role in the behavior of the system. And let me give you an example again that's drawn from epidemiology, from the spread of disease. Here's a figure that I showed you early on. That was from this study of the spread of tuberculosis. Now, you can see that there are hubs in this network. For instance, there's this node in the middle that has 100 connections or something like that. You can immediately imagine that that could have a big effect on the spread of disease. If that person gets sick, then they could give the infection to a lot of other people. But it's worse than that, because that person is also more likely to get sick in the first place, because there's 100 people they could catch it from, and then 100 people they could pass it on to. So they're 100 times 100 or 10,000 times more effective at spreading the disease than the person who only has one connection. So this turns out to be a huge effect. It means that these hubs can dominate the behavior of the system. The person who has 1,000 contacts is 1,000,000 times more effective at spreading the disease than the person who only has one. So to give you an example of that, so here's an example from real life. This figure shows data on the original SARS, the outbreak of coronavirus that they had in Southeast Asia in 2002, 2003. That one, thankfully, did not become a worldwide pandemic, although there was some worry about it at the time. This figure here shows data from the outbreak that they had in Singapore. What you're seeing on the left there is that node marked number 1 on the left is the first one they know about, and unfortunately, that node was a hub. They have lots of connections. They gave disease to lots of people. Most of the people they gave it to are not hubs, which means that it didn't spread any further. Maybe it didn't give it to anybody else, or maybe only one other person. But the disease would have died out at that point if it weren't for the fact that one of the people that number 1 passed it on to is number 6 there. That's another hub, gives it another big boost, spreads it to lots of people. Again, most of those people are nobody special, didn't pass it on to anybody, except for number 35 there. Another hub gives it another big boost, and so forth. What you can see is these hubs, even though there are only a few of them, are just enough that they're keeping the disease alive. So they're basically single-handedly responsible for keeping this infection spreading. This immediately suggests possible strategies for controlling the spread of disease. If you could identify these hubs and, for instance, vaccinate them against the infection, then that would be an extremely efficient way of preventing the spread of disease. You'd only have to vaccinate a rather small fraction of the population, and you could stop the disease dead in its tracks. All right, very good. So those are 2 examples of sort of classic results in the field. In the last few minutes, I would like to tell you a little bit about stuff that we've been doing in my group here at U of M. People often ask me when I give talks about this stuff, they say, so what do you actually do? Like, on a day-to-day basis, what are you doing? Well, first of all, I'm not wearing a suit. But it's a fair question. What do we actually do? So I'm a theoretical physicist by training, and my work applies methods of theoretical physics, which means mathematical and computational modeling, to the study of these network systems. So what I'd like to do in these last few minutes is give you an example of the kind of things that we do. There's going to be a little bit of math in this part of the talk. However, don't worry. If you're not a math person, I think it should be fine following the gist of the argument, even if you don't follow the math in detail. I'm going to, again, focus on the spread of disease, the example that we've been using throughout here. And I'm going to ask a new question. I'm going to ask, suppose I have some disease spreading through a population, like COVID, for instance. What is the risk to a particular person? What is the probability that that person will get the infection? Okay, so that's obviously something that matters to us personally. It depends on where you are in the network. If you're out here, out on the edge of the network with just one or two connections, then you're not at much risk of catching the disease. If you're right in the thick of things in the middle of the network, then you're at much higher risk. So where you are in the network absolutely affects your disease risk. So what I want to do is a calculation of that. So now I'm going to make the point here that in order for you to catch the disease from one of your people that you're connected to, one of your network neighbors, two things have to be true. First of all, they have to have the disease. And second of all, they have to give it to you. That's illustrated in this figure here. The red nodes are the ones that have disease, and then the red edges are the ones that the disease is being transmitted along. Both of those things have to happen. In the jargon of the field, we talk about contact sufficient to transmit the disease, right? I may have a friend, but I didn't see them this week. So even if they had the disease, they wouldn't have transmitted it to me. So I have to have contact sufficient to transmit the disease, and they have to be infected. Okay, so let's say there's some probability that I have contact sufficient to transmit the disease. We'll call that probability P. Okay, so now I can turn this into an actual calculation. I can say, what's the probability that I get the disease from my friend? Actually, it turns out to be easier to calculate what's the probability that I don't get the disease. So let's do that. So here's how it goes. First, I have this network. I'm just going to number all the nodes. Say there's 100 nodes. I'm just going to number them 1 to 100. Any order, it doesn't matter. I just want to be able to say which one I'm talking about. And then I'm going to define a quantity, ui, which is the probability that I is not infected with the disease. Okay? So now I ask, what's the probability that I does not get the disease from their neighbor j? There are two ways that could happen. One is they don't have contact with their neighbor. In that case, the disease is not going to get transmitted. If P is the probability of contact, then 1 minus P is the probability of not contact. The other thing that can happen is you do have contact with them, probability P, but they themselves don't have the disease. That happens with probability Uj, because Uj is the probability that they don't have the disease. That's how it was defined. So this whole expression here, 1 minus P plus P times Uj, is the total probability that you didn't get the disease from your neighbor J. Now I want to know what's the total probability that I didn't get it at all. I just take the product of that probability over all of my neighbors, just multiply them all together, and I get the total probability that I did not get the disease. So this equation here now tells me the probability U sub I that I didn't get the disease. So now I have an equation that allows me to calculate these risk probabilities for all the people in the network. Actually, it's not just one equation. This is one equation for every node. So I have to solve this huge big system of equations. How do I do that? Well, there are a variety of ways of doing it, but the easiest way of doing it, it's a very simple way of doing it, is you just guess random numbers for all these U variables. You plug them in on the right-hand side of this equation. It gives you new numbers on the left. You take those and you plug them in again, and you just keep going on round and round and round until the thing settles down and the numbers stop changing. And when you do, that gives you a solution to the equation. So you can do this. I did that here for that very same network that I just showed you on the previous transparency, and then I colored in the nodes to show their risk of infection. And indeed, what you see is round the edge, low risk of infection, that's the red colors, middle of the network, high risk of infection. So indeed, it depends where you are in the network. Okay, so now that I've done that, turns out there's a whole bunch of other things that I can calculate. A simple one is, well, if ui is the probability of not getting the disease, then 1 minus ui is the probability of getting the disease. Add that up over all of the nodes in the network. That just gives me the average number of people who get the disease. So now I can tell you how far this disease is going to spread. I'm going to tell you how many people get it in total. Very useful thing to know. Here's a more subtle question. Is the disease going to spread at all? Sometimes diseases don't spread. It depends on the value of that P, the probability of contact. Look at this equation here. If I set all of the variables u to 1 in this equation, I get a solution. I get 1 minus p plus p. That's just 1. So I just get 1 times 1 times 1 times 1, which is just 1. So that's a solution, right? So there's always a solution to this equation, which u equals 1. What does u equal 1 mean? Well, u, remember, is the probability of not having disease. So if u is 1 for everybody, then nobody has disease. Disease is not spreading. That's always a solution. So does that mean that the disease never spreads? It does not. Because it's not just a question of whether that solution exists, it's also a question of whether you go to that solution. Remember, the way we're solving it is we're just iterating this equation until it converges to something. The crucial question is, do you converge to that solution, no disease, or to some other solution that says you have got a disease? Another way of saying that in mathematical terms is this an attracting solution or a repelling solution? And there's a nice mathematical technique called linear stability analysis that can answer that question. So we apply it to these equations here, and it says an interesting thing. It says if P is sufficiently small, no disease, doesn't spread. If P is large enough, disease does spread, and in between there is a sharp threshold called the epidemic threshold at which the disease starts to spread. So you get this sort of characteristic behavior where you get no disease, no disease, no disease, and then suddenly you go through this threshold and it starts to spread. And when it does spread, we can tell you how many people are going to get it. Okay, so now we have this, there's all sorts of other things we can calculate. We can calculate the position of that threshold. We can calculate the so-called basic reproductive number, R0, which you may have heard of. It's been in the newspapers a lot. It's a basic parameter of the disease. We can calculate the herd immunity threshold. How many people would have to get vaccinated in order to prevent the spread of disease? And then this can allow you to judge the efficacy of various public health interventions. For instance, this equation here that tells you the value of the threshold says, how high does the contact probability have to be in order for the disease to spread? If I want the disease to not spread, I should lower my contact probability so I go below that threshold. How could I do that? I could do that, for instance, by encouraging people to wear face masks. That's what that does. It lowers the probability of contact sufficient to spread the disease. You don't have to lower it all the way to 0. You just have to get it below this number, PC, and the disease will stop spreading. An alternative approach is you could keep your probability the same, but you could raise PC. That would achieve the same thing. One way of doing that is to decrease the number of edges in your network, the number of contacts that people have. You can do that, for instance, by social distancing. And you can use these kinds of results to say precisely how big the effect is going to be when you do all of those things. Okay, so I'm out of time here. I should stop talking. I hope I've convinced you that there's interesting questions here. This is a big and vibrant field, lots of people working in this area, although there's also many questions that we don't yet understand and have answers to, so there are many opportunities to do things in this field as well. Just before I finish, brief personal note. I've been here at U of M for 20 years now. It's been a terrific time. This is a terrific place to work. And one of the reasons why it is a terrific place to work is because of the many fabulous colleagues and scientists that I've got to collaborate with while I've been here, including faculty colleagues shown along the top in this slide, and the many brilliant graduate students who've come through my research group over the years. Science is not done in a vacuum. This is a collaborative enterprise. It is a huge honor to receive this Henry Russel lectureship, and I share this honor with all of these people because without them, none of this work would have been done. So a huge thank you to them. Thank you also to all of you for listening, and I'd be happy to answer questions if you have them.
Thank you very much for a wonderful and very accessible lecture. We have time for questions. We would ask that there's microphones, so if you could raise your hand, a microphone will come to you, and then if you would take the question. So somebody will be willing to lead us off? Right in the front here, Kira.
Thank you so much for that. That was really wonderful and fascinating. I will confess I'm not a mathematician or a scientist in any way, but I was wondering how much your work is in relationship with data visualization and how much data analysis is part of the work that you do. Because I also understand that to be its own kind of separate world and field where people also have arguments about how to represent the data that they've found.
So that's an excellent question. Yeah, so there are really sort of two sides to what we do. One is the sort of mathematical side that I discussed here, where we're modeling and making predictions about things. But there is also a whole data analysis side. You're absolutely right. I showed a lot of pictures that were based on data for real networks. And although I'm not an experimentalist, I don't go out and collect the data myself. I work with people that do. And then we do a lot of work on analyzing the structure of real networks and trying to say something about those systems, often sort of in tandem with these mathematical theories. So absolutely, there's sort of two halves to the work, one of which is mathematical theory and one of which is data analysis, and we try and bring those together.
Question in the back?
Yes.
From online?
Thank you. We actually have one off the live stream. A lot seems to depend on the structure of networks. What determines that structure?
So the question is, what determines the structure of the network? So many different things, and it depends on different kinds of networks. So some networks, their structure is determined by some growth process. You're sort of adding nodes to them one by one. So the internet grew from small to being large. A citation network grows as more papers are published. And that can have distinctive signatures in the structure of the network that you end up with. Other networks, such as the airline network that I showed you, are more about optimizing some objective. They're like, we're an airline, we're making a network of flights, we're going to put the flights in the most efficient places possible in order to get our customers where they need to be whilst not spending too much money on airline fuel and things like that. So there are different processes that give rise to the networks depending on which one you're talking about. If you're talking about the biological networks, then presumably it's an evolutionary process that has been at work over millions of years to determine what the structure of that network is, and so forth. So people have studied all of these things, and there are a range of different theories, different ones applying in different circumstances, depending which network we're looking at.
Question here in the front. Microphone's on its way.
Hi, Professor Newman. Thanks for your brilliant lecture. I'm an undergrad student here at Michigan, and as you might know, as the foundation of machine learning, artificial neural networks is also a part of networks. How do you see that connect to your research?
So the question is, what's the connection between our research and artificial neural networks? There has been, so a lot of what we do is looking at empirical data for networks, which is not directly connected to artificial networks, but there has been a lot of work in network science looking at actual neural networks, neural networks in the brain or in the brains of animals. So there's been a lot of data work done on that and a lot of modeling work done on that. And some of that has inspired work on artificial neural networks. There are also variants on neural networks, such as so-called graph neural networks, that are based on sort of generating networks and then placing neural networks on top of them. And there is work, particularly in computer science, sort of theoretical work to try and understand what's the connection between the structure of those networks, those artificial neural networks, and their dynamics and the way they behave, which could lead to things like, can we design the structure to better do a particular job? So there definitely are connections there, but I think there's also a lot more to be done in that area.
Question here. Sharon? There's a microphone.
Where was it?
No. No, please use a microphone because of the online. Thank you.
Thank you, Mark, I aspire to lecture as well as you do. You mentioned at the end that there are questions that network scientists still haven't answered, and that there are opportunities. What are some of them?
What are some questions that we haven't answered? So I think that one big area for me is to do with how networks change over time and how that affects the behavior of these systems. So everything I talked about, I was sort of assuming the network is just a fixed thing that we're given. But in actual fact, all of these networks are changing over time. Even if it's a biological network, like a metabolic network, it's changing on evolutionary time. And others, like the social networks that determine the spread of disease, can change on a daily basis. So how is that going to affect the spread of disease? So in order to do that, we would have to sort of generalize our models of network structure to temporal change of networks. And we would also have to understand how the processes going on in those networks change now that the network is changing underneath them. And I think that there's a whole set of interesting questions there to do with these aspects of dynamics in these network systems. There's many other things as well that are interesting to work on, including many problems to do with, for instance, neural networks and learning systems, problems to do with ranking problems to do with spectral graph theory. My own work, I've done a lot of work on message passing methods. I think that there are large areas, both of theory and of practice, that we don't understand well. Yeah.
Question here in the front, and then one right behind.
Hi, thank you very much for your presentation. Could you talk a little bit about how do you manage the complexity of doing the analysis that you do? Like, if you have an airline network, that's probably a few hundred nodes, but if you have billions of people and you're trying to find a fixed point, that may take a while. Do you use abstraction? What do you do to manage that?
Okay, very good. So the question is, how do you manage it when these problems become very complex? When you have a very large network, for instance, the World Wide Web with billions of nodes, what can you do? So we work on various things that touch on that. One is that we do algorithm development, meaning we work out ways of analyzing these networks, and a big part of that is coming up with algorithms which will not only work, but will work fast, because the networks we have to apply them to are very large. Another thing that we do is we look at ways of breaking networks apart into their parts so that we can sort of do a divide and conquer. We can break them down into smaller parts and then study the smaller parts instead of having to study the whole. There's a whole area within network science that I've been heavily involved in called community detection, which is about, if you give me a network, how can I sort of find the natural fault lines that it breaks apart along so I can divide it into its separate parts and then study those individually. So that also gives us a way of taking these very large problems and boiling them down into smaller ones.
I think there was a question. Yep.
Thank you for being here. I was a student here in 2008 and very briefly had a chance to meet and study with Carl Simon and learned about complex adaptive systems and was introduced to this mystical place, the Santa Fe Institute. And still, I'm hoping to get there someday. How does your work intersect and complement the work being done in complex adaptive systems?
Yes, so an excellent question. So in addition to having an appointment in the physics department, I have an appointment here at U of M in the Center for the Study of Complex Systems, where we do exactly that kind of work. I would say that the network science that I'm doing is one of the most prominent branches in modern complex systems theory. There are other important branches as well, such as dynamical systems, information theory, game theory, computational complexity theory, that go together to make the larger set of topics that we call complex systems. But this network science has very much become, over the last 25 years or so, a central plank in complex systems study, because complex systems is about systems made up of many interacting parts. And it turns out that the pattern in which they interact, which is the network, is very important in addition to the way they individually behave. So that this idea of studying the structure of the network as well as studying the behavior of the individual parts turns out to be very important for understanding all sorts of things, such as these disease spreading problems. So I would say that this is a part of the broader study of complex systems, something which is represented strongly here at the University of Michigan in our Center for the Study of Complex Systems.
Great. I think we have time for two last questions, one here and then one last one.
Yeah. Thinking of social problems, let's say teen suicide or veteran suicide, can you lay out steps that might be used to develop a structure of potential network? You know, intuitively, it seems like there's a lack of network that would be involved with those kind of issues. But have you run across any networking in those areas?
So the question is, how could we think about the structure of networks relevant to helping social problems? And I think that, in your question, you're sort of maybe hinting at the idea of maybe we could sort of design the network or create a particular structure of the network would help. I think that we're not there yet. So that's actually an interesting area, the idea of sort of designing networks to have a particular behavior. At the present point, we're more at the level of characterizing the networks we see and understanding how that structure results in the behavior that we see. So we could maybe answer questions like, what's wrong with these networks? You know, do they have weak points or problems? I think the question of whether we could work out what's the best way to create a network that would help people in a certain way is one of these open questions. I think that's a really interesting and important question, but I think at present that's further than we've got in this field.
Thanks. And our last question here. There's a microphone right behind you.
So how would a network apply to something like Beethoven's Ode to Joy? The music and the way it's all organized and so on.
Can you repeat the question?
So the question was, how would a network relate to a piece of music? The example given was Beethoven's Ode to Joy from the Ninth Symphony. So that's an interesting question. So I enjoy music. I teach the physics of music here at the University of Michigan. And I have often thought about whether there's a connection between my interests in music and my interests in networks. Some people have looked at connections there. For instance, transitions between chords or harmonies. There was a famous paper in the 90s. I have a collaborator, Dmitry Timochko, who's a composer at Princeton, and he wrote a paper in the 90s about transitions between chords in music, which sort of falls into some high-dimensional space, and he looked at the group theory of this thing. So some people have looked at stuff like that. I think there's definitely connections between complex systems, more broadly construed, including especially dynamical systems theory and music. I think that the connections between music and network theory are not obvious to me at present. But if I could find one, that would be great, because it would allow me to bring together these two things that I like very much. Good question.
Thank you very much, Professor Newman, for this great question and answer. Please join me in thanking our Henry Russell lecturer, Professor Newman.
Thank you.
I now invite you to stay for a reception in this room. Thank you very much for attending this afternoon.